Okay, this is 9.1 homework. The first problem wants to find the number of distinguishable permutations of these letters right here. So the formula for that I gave you in the notes and included the book pages on the website as well. The formula for that is n factorial divided by n1 factorial times n2 factorial, where n is the total number of numbers, which in this case is 3 plus 3 is 6, 7, 8. So the 8 factorial divided by, and these numbers in the bottom are the letters that repeat and the number of times that they repeat. So n1 would be 3, representing there's 3 a's here. So it'd be 3 factorial, and then there's 3 to represent the b's as well. So it'd be times 3 factorial. So that would be our answer for the total number of distinguishable permutations, which is 1120. And this makes somewhat sense because this is the total number of permutations, the total number of ways you can rearrange 8 letters. But we do have to divide out the ones that are the same. So this 3 right here, there's 3 ways in which, there's 3 factorial ways in which they're the same, because these letters, when you change them, there's 3 factorial ways you can change these individual letters and keep them in the same spot, so you wouldn't know the difference. So you have to divide that out. Same thing with the b's. Now the next part says if permutation is chosen at random, what is the probability that it begins with at least 2 a's? Now we're actually not going to cover probability to the third section, but this is a good question because it still has to do with the counting, especially the distinguishable permutations. So if a permutation is chosen at random when it starts with 2 a's, then we have 2 a's to start with, and now the question becomes, we've got 2 a's, so we've got these letters left to choose from. So how many ways can we then randomly choose those letters? Well, there's 6 left, so it'd be 6 factorial. We have to divide out the ones that aren't distinguishable, which are the b's here, and there's 3 of them, so we have to divide out 3 factorial. So this gives us 120. And then for probability, we have to take the number that we're looking for divided by the total, which we'll talk more about soon. So that's our answer, 120 over 1120. Okay, the next problem wants to find the value of this permutation. This is 9p3, and we can do this in the calculator by hitting 9, going to math, scrolling over to probability, and then going down to 2. And then that puts the p there, and then hit the 3, and you get your answer, which is 504. Another way to do this is with the formula right here that I gave you guys in the notes and in the book. It's 9 factorial then over 9 minus 3 factorial, which would be 6 factorial, which gives you the same 504. Okay, the next problem says how many 3-letter words can be made from these 10 letters here. The first one, if repetition is allowed. Well, if repetition is allowed, we have 10 letters to choose from for the first one. Then we have 10 letters to choose from the second one, and then we have 10 letters to choose from the third one, so that'd be 1,000. If repetition is not allowed, then we have 10 letters to choose from for the first one, then we only have 9 left, and then we only have 8 left. So it'd be 9 times, or 10 times 9 times 8, which is 720. Okay, the next problem says in how many ways can 9 students be seated in a row of 9 chairs if Jack insists on sitting in the first chair. So we have, imagine 9 spots to choose from, but Jack's going to sit in the first one, so that's already taken care of. So we have 8 people left to choose for 8 chairs, so it'd be 8, for the first chair, and then you have 7 left to choose for the second chair, and then 6, and so on. So you end up with 8 factorial as your answer, and you can enter that in as 8 factorial like that, or do it in your calculator. In your calculator, it's 8, and then math, probability, and then factorial is 4. And that gives you 40,320, which also works. All right, the next problem, we're choosing 3 letters from 6 letters. So we have 3 choices. We have 6 for the first choice, 5 choices for the second, and 4 for the third. So that gives you your answer of 120. You could also do 6p3 because you're choosing 3 letters from 6. What order does it matter? That would also give you 120. Okay, the next problem says how many different 8-letter permutations can be found. We're choosing from 6 identical h's and 2 identical t's. So if you wrote this out, it's with the t's in the end, it's similar to what we had before, where we have 8 factorial divided by the 6 factorial for the repeating h's times the 2 factorial for the repeating t's. So this is the distinguishable permutations formula, which gives you your answer of 28. In the top goes the total number of ways you can choose these letters divided by the repeats in the bottom. Next problem says how many ways there are to seat 4 people in a row of 6 chairs. That's 6p4. We're choosing 4 people from 6 different spots basically because the 2 empty chairs can be interchangeable. Another way to look at this is to do there's 6 factorial because you're choosing 6 spots, including someone not sitting there is still a choice, but you have to divide out 2 factorial or just 2 because you have to divide out the empty seats wherever they end up being. So that's empty and that's empty. Those are interchangeable and so they're non-distinguishable. So we'd have to divide those out using our distinguishable permutation formula. Either way, you get 360. Okay, the next problem says there are 9 different positions in the baseball team. If there's 15 players, how many different lineups can we make? Well, you can look at this as you're choosing 9 spots, and you start off with 15 choices for the first, then you have 14 left, and 13, 12, and so on. But you could also do the permutation. So you're choosing 9 from 15, where order doesn't matter. Either way, you get this really big number right here, about 1.8 billion. Next problem says a boy has 4 red, 4 yellow, 5 green marbles, and how many ways can they arrange the marbles if the marbles the same color are indistinguishable? Well, we have 8 plus 5, so we have 13 total marbles. So there's 13 ways we can rearrange them, but we have to divide out the ones that are indistinguishable using the distinguishable permutation formula. So the ones that are indistinguishable are the red ones, the yellow ones, and then also the green ones. And there's 4 for yellow, 4 for red, and 5 for green. So there's the formula. That lends itself to 90,090, which would be our answer for A. And then if all the marbles have different sizes, then we don't have to divide out any of the distinguishable, non-distinguishable ones. So we just have 13 factorial here, which you can enter in just like that if you want. Next one's pretty easy. We have 6 runners. How many ways can they finish? Well, that's just 6 factorial. For first place, we have 6 choices. For second place, we have 5. For third place, we have 4, and so on. You end up with 6 factorial. Next problem says a true. So if you have 21 questions, you have 2 choices for the first, 2 choices for the second, and so on. So you end up with you can just keep going to 21. You end up with 2 to the 21st power then, which is 2097152. Okay, the next problem says we have a lottery game. We're going to pick 6 numbers from 55. How many different choices does the player have if repetition is not allowed? If repetition is not allowed, then we have 55 choices for the first, 54 for the second, 53rd, and you get the idea. 6 letters. So that's the same thing as doing a combination. You're choosing 6 from 55 where order matters. So you get the same answer if you do 55C6, which is on your calculator if you just do 55 and then go to math over to probability and down to the third one and then hit 6. You get this number here, which is your answer. All right, the next problem says you own 24 CDs. You want to arrange 6 from the CD rack. What's the probability they end up in alphabetical order? The probability is there's only one way they can end up in alphabetical order, so that's the total number of ways that we want, divided by the total. The total is you're just arranging 6 things. So it's going to be 6 factorial because you have 6 to choose from, and then you have 5 left, 4, 3, 2, 1. That's the number of ways you can arrange 6 things. The 24 CDs kind of throws you off, but that's not useful in this problem. So it's 1 divided by 6 factorial. Okay, the next problem says we have 10 red marbles, 9 white, 9 blue. We're going to draw 5 at random. We want to know the probability that all are red. Well, if all are red, we're choosing 5 from 10 divided by the total, which would be choosing 5 from 28, where order doesn't matter. Combinations is when order doesn't matter. I think I messed that up earlier in the video. But we want to use combinations here. Actually, permutations would work as well because you're dividing, so it ends up being the same whether you use permutations or combinations. But this is the right way to do it. It gives you about 0.0025641. Okay, the next part, if we want exactly 2 red marbles, then from 10, we're choosing 2. And then we also have to choose 3 more from the remaining 18. So it'd be 18, choose 3, where order doesn't matter, divided by the total, which once again is 28, choose 5. That gives you the right answer of 0.3736. And then the last one, we're going to choose the marbles that none of them are red. That's 18, choose 5, because there's 18 marbles that are not red. And then divided by the total, 28, choose 5, where order doesn't matter. That gives you about 0.0872. Next problem says a pizza parlor offers the choice of 16 toppings. How many 6 topping pizzas are available? We're choosing then 6 from 16, where your order doesn't matter. And so that's a combination. You get 8,008. Okay, the next problem says a school dance committee. We're going to have 2 freshmen, 3 sophomores, 4 juniors, and 5 seniors. And we're choosing from 7 freshmen, 7 sophomores, 9 juniors, and 7 seniors are available to choose from. So that ends up being this right here, where we're choosing 2 freshmen from 7. We're choosing 3 sophomores from 7. We're choosing 4 juniors from 9, and we're choosing 5 seniors from 7. And if you multiply that out, you get your answer, which is about 1.9 million. Next problem, 9C4 is what we want to do because we're choosing 4 books from a group of 9. Order doesn't matter. That should give you about 126. All right, the next problem says how many 5-card hands consisting of 2 kings and 3 aces can be dealt from 52 cards. There's 4 kings, so if you're choosing 2 of those from 4, there's 2 cards in your hand. And then there's 4 aces, you want to choose 3 of those from 4, and that will be your 5 cards, which gives you 24 as your answer. Okay, the next problem wants you to do 7, choose 1, 10, choose 10, 12, choose 8, which, like I said, I usually write like this. But we can do that right in the calculator. Just do 7 and then hit math. Scroll over to probability, scroll down to choose again, which you will probably already know this, but hit 1, that gives you 7. And if you do the same thing, you get 1 for this one and 495 for the last one. Okay, the next problem says a boy has 3 red, 5 yellow, 5 green marbles, and how many ways can we arrange them if all the marbles of the same color are indistinguishable? So that'd be 13 marbles total, so there's 13 factorial ways you can rearrange them, because you have 13 choices for the first one you pick to arrange, then 12 for the second, and then 11 for the next one, and so on. But you have to divide out the ones that are indistinguishable, which in this case there's 3 red ones that are indistinguishable, 5 yellow ones, and also 5 green ones that are indistinguishable. So you have to do this, which gives you 72,072 different ways. Okay, and the last problem says a 5-card poker hand is dealt from random 52. What's the total number of possible hands? So you're choosing 5 cards from 52, where order doesn't matter. That gives you the first answer right here. And the second one wants the total number of possible hands that contains exactly 1 heart. So with 1 heart, there's 13 hearts. We're choosing 1 of those, so that's actually 13. Times the other 4 cards from the remaining. So there's 30 cards remaining. We're choosing 4 more from those. So that would give you the total number of possible hands then, which would be a little over 1 million, this number here.